So in the last lesson, we talked about experiments. And the four main components of a good experiment, which are, without looking, control, replication, comparison.
That's another scene.
No, not another scene. Random assortment. Did you look?
No.
Okay, yes. So that makes, those are what make a good experiment. And we also talked about how to sort of briefly describe a completely randomized experiment. Sometimes we may want to do, it's still randomized experiment, but we may want to change things a little bit the way we set up the experiment, okay? And this is by something called blocking. So here's the Jennifer John study again. This is just a repeat of what was in the last lesson about how they went about trying to find out if there was any hiring discrimination based on gender. Okay? So imagine the experimenters, they got just 8 faculty, okay? 8 faculty members to evaluate the applications, and 4 for John, 4 for Jennifer. One would assume they randomly assign them to the groups. And then the hireability ratings from the faculty are shown to the left there. So you can see here are the 4 hireability ratings for John. Here are the 4 for Jennifer. Would you say that there's substantial evidence of hiring bias? Not really. I mean, there's an advantage for John, a little bit, but that maybe have been just due to chance alone, the way the people were randomly assigned into the groups. So yeah, that would be the best answer for this one. Okay. No, because there is a minimum advantage for John that may have been caused by chance in the random assignment. Why didn't we use that before? But let's say we dove a little deeper into this, and we found out that of the 8 faculty members, okay, 4 were from a tier 1 or more prestigious university. 4 were from a tier 2. So we decided to look at, okay, well, before we look at the entire picture of all the faculty members, let's break it down by tier 1 professors and tier 2 professors. And we can see here, so here are the tier 1s. They've rated both of them lower than the tier 2s, okay? Do you see more evidence of discrimination here? Yeah, because there's not, like in up here, you know, you have this overlap where really neither had an advantage. But here, if you look at it, there's very little overlap in the purple, like probably doesn't look like any really, and same with the orange X's, right? it seems to be more clear that the faculty members prefer John, right? So we would probably say yes. Make sure I get this right. Because when broken down by tier, John has a more distinct advantage. Seems to be a little clearer. So what does this mean? This means that when we do an experiment, sometimes we may sort of have to separate the people we're doing the experiment on, the individuals or the subjects, into groups that perhaps they share some common characteristic, because that could affect the results of the experiment. So here, like I said, I mean, if you just looked at them all as professors or faculty members, there didn't seem to be a difference. But as soon as you group them according to the quality of university they taught at, it seemed there was a difference. Okay. So when we break it down and analyze it like this, what we are doing is blocking. Okay, so if we want to break it down by school tiers, not just faculty members, we would do a randomized block design. Okay? So experimental units are first blocked or grouped by some similar trait. Okay? This is very similar to stratified random sampling. Okay? It's kind of the stratified sampling of experiments. Because remember, when we were trying to choose samples, we talked about, well, maybe the population that we're randomly choosing from, there are groups within that population that may have differing opinions about something, or may have different characteristics, right? Same with experiments. And so what it does is it reduces the variation between the treatment groups. So it makes it easier to show that the differences in responses are really, what do I want to say there? It makes it show that differences in responses are really due to the treatment rather than the chance variation, or due to the experiment that took place. Okay. Okay. So just like in the last lesson, we described a completely randomized experiment. You could be expected to describe a randomized block design experiment. So how would you implement it for the Jennifer John study? Assume, let's make the assumption, we'll use easier numbers. We've got 12 faculty to choose from, 6 from tier 1, 6 from tier 2. And that you're going to block by university tier. So there, oh yeah, there's 6 in each one. Okay. So what would you do? How would you start assigning, randomly assigning? Like how would you, what would you take with the 6 guys from tier, or 6, not guys, people from tier 1? Give them all a number from 1 to 6. Pick 3 of random numbers. They go to John. The other 3 go to Jennifer. Repeat with the second tier faculty members. Okay? So take the 6 tier 1 and number them from 1 to 6. Randomly select 3 numbers. Assign those people to the John group. Remaining 3 go to the Jennifer group. Okay. Repeat the process for tier 2. Repeat the process for tier 2 members. So there are 6 members of each group. Okay, so got the groups randomly assigned. We've blocked them. Now what do we do? You do have to add a little bit more. Once we're ready, what do we do with them? Give them the treatment, which in this case, give them the resume, have them do the hireability rating, and estimate the salary. So apply the treatments, which in this case are the resumes. And compare hireability ratings hireability ratings within each group and overall, which is what we saw on the first page. So we see what's happening overall. We want to see what's happening within the tier 1s and within the tier 2s. Okay? And then hopefully out of comparing all of that, we can make some sort of conclusion or not. Okay? So that's a randomized block design. A type of randomized block design, and students do have difficulty with this one. Is a matched pairs design. Matched pairs is when you don't have 2 big groups, okay? You have one-on-one, or one person against themselves. Either of those make a matched pair design. So each block is composed of, where am I here? Word here. 2 similar experimental units. But often the matched pair is simply the same experimental unit receiving both treatments. Okay? And the order of the treatments is randomized. So let's say, for example, you wanted to Okay, when Emily's here, there's 14 students here. Okay. So let's say I wanted to test whether music improves results in AP statistics. Okay. So what I do is I say, okay, I'm going to randomly assign 7 of you to do this AP worksheet, this assignment, while listening to music. And the others, you're not going to listen to music. You're going to complete the exact same as I'm going to control it. And I have 2 comparison groups. And 7 in each group is a decent size. So replication seems to be accounted for as well. Okay. And then, so then I see what happens. I mark the assignments and then see if there's any difference in the music group and the non-music group. Okay. That is a randomized design. Okay, for sure, completely randomized. However, what if I said, okay, I'm going to take your marks right now, what your marks are, and I'm going to say, okay, whoever the top 2 marks are, I'm going to put you guys into one group, and I'm going to say, okay, I'm going to flip a coin and say, you're going to listen to music and do this assignment, you're not going to listen to music. And then I'm going to take another pair of you, and another pair, and another pair, and another pair, until I have 7 pairs. That's a match design. Okay. Or what I could have done is take each of you individually and say, okay, this is what we're going to do this week. You're going to do 2 assignments for me. And I'm going to flip a coin as to whether the first assignment you do, you get to listen to music or not. And then I'm going to compare how you did on each assignment. That is also a match pairs, but you're matched against yourself. So you could be matched against another person or another subject, object, or whatever, okay? Or you could be matched against yourself. So make sure you understand the difference. So here's another example. In this study, researchers wanted to test if taking a fake pill would actually alleviate depression symptoms, even though the pill had no active ingredients. So we would call that pill a placebo, right? So 35 people volunteered to take part in the study, all had major depression. None were taking any medications. Because depression varies greatly between individuals, the researchers implemented a matched pairs design. So there's a couple of ways you could look at this. Although there's 35 people, so it may be difficult to pair completely, right? So let's say you're not going to pair off people. Like you would say, give them a test or something and then take the 2 most depressed people and then give one of them the fake pill and one of them has nothing and see what happens. Let's say we're going to do it. They're going to do it against themselves. How would you do it? Emily?
You give them the both. So say they're taking it for like a month.
Yeah.
2 weeks of those pills would be like those, and it takes a lot because even if you're on the so you would double the 50 million.
Well, actually, in this one, I believe you're either taking a pill or you're not taking a pill at all.
But you're taking up this.
Yes, in one of the groups, but in the other group, you're not taking another one. Like the idea is to see if the fake pill, which apparently is advertised as alleviating depression, nobody's taking a real pill. You're either taking a placebo or you're taking nothing at all. So you're right. You would, like say for a 2-week period for each person. How would you decide whether they take the fake pill or no pill first? Yep, flip a coin. It's got to be random. Okay. And so, yeah, so let's say they take the fake pill first. So they do that for a couple of weeks. And then there's some kind of test to measure, like maybe there's a, oh God, I can't think of the word. When you want to measure somebody's depression level, you give them not a survey. What am I thinking of? I'm thinking of something. Assessment, yeah. Evaluation, yeah. All of those are right, but why am I thinking of another word? I don't know. That's why I'm asking. I'm sort of like throwing it out there to see if somebody. Calissa, I don't know. Oh, now she does though. Okay, fine.
Like, is it a specific one? An example? Oh, it's like, yeah,
No.
a standardized questionnaire.
Questionnaire. Thank you. Sorry, I didn't mean to scare anybody there. I don't know why. I didn't think I was just drawing a blank. Okay. Or maybe you give them an MRI. Measure brain activity. What's happening in the brain? Okay, so how do we say this? For each subject. Flip a coin. To determine whether they get a fake pill first or no pill. After a while, or after, I don't know, after days, switch to treatment. Measure their depression using some instruments, questionnaire, MRI, measure their depression level. And compare results. Individually, like for each individual and a whole. Okay. So this was a study that was actually done. And what happened as a result of this study? Well, people reported that they were less depressed after they took the fake pill, rather than taking nothing at all. Okay. And they showed, well, this is fancy science stuff, increased opioid receptor brain activity in regions of the brain associated with emotion and stress regulation. So what happened is the belief in the pill caused change. Okay, and it caused a biochemical change. However it was measured. And this has happened in numerous studies with things like migraines, blood pressure, etc. that you see there in the list. Okay, where even though it was fake, there was no active ingredient, there was nothing that was treating whatever the issue was. It caused a change. Okay, and so when we administer a fake pill or a fake treatment, that's called a placebo. And if a change comes out of it, that's called the placebo effect. Okay? So a placebo is an inactive treatment. And the placebo effect is when the subject's belief of receiving an active treatment leads to a measured response, even though the treatment is, what did I write here? Sure I have the right words. Actually inactive. Now that previous study was actually measuring the placebo effect. Okay, but what if we don't want that to happen? What do we have to do? We either have to do a single blind study or a double blind study. Okay, so in a single blind study, either the subjects or the researchers are unaware of who receives the active treatment or placebo. And normally, like when we want to test to see if maybe some type of medication has any kind of value, you get the actual medication and the other group gets a placebo. Okay. And usually it's if you're only going to do a single blind, it's the subjects that shouldn't know. Okay. But to get even better, double blind. Okay. Neither the subjects and the researchers are aware. Because there are people out there that want a certain type of result and will do things to push some type of experiment in their favor. Okay? That's why it's so important when people are doing experiments on the benefits of new drugs or something like that, that they have to come out with a very detailed explanation as to how they went about testing it. Otherwise, they'll get accused of trying to push an outcome that they wanted or that somebody else paid them to get. So why is it beneficial to blind subjects? So the placebo effect is reduced. And why is it beneficial for blind researchers? To avoid a biased outcome. So that pretty much sums everything up that we're going to do. There's just one more thing to look at. And I talked about this before. When can we say something causes something else? We can only say that something causes something else if we randomly assign subjects to groups. If they were randomly assigned, we could make a conclusion about cause and effect. Remember, we're only taking a sample too, right? We're not taking an entire population. When can we not apply it to the entire population? When can we apply it to the entire population that we sampled from? It depends. How did we get the individuals in the first place? Okay, were they randomly selected, or did they volunteer, or were they appointed? That makes a difference, right? And you can see this table here kind of sums it all up. So if subjects were randomly assigned to groups, and, sorry, I'm going to use this first. If they were randomly chosen from a population and then randomly assigned to groups, we can make a conclusion about cause and effect and apply it to the population that we sampled from. I'm just going to jump over to this one here. If we did neither, then you can do none. Okay, if we did not randomly sample from a population and did not randomly assign them to groups and conduct an experiment, we can't make a conclusion about cause and effect. We can't generalize it to the population we sampled or we got the people from. How about this one? They were randomly sampled from the population, but they weren't randomly assigned. Can I generalize to the population? Yes, because of this. Can I make a conclusion about cause and effect? No, because of this. And then this would be the opposite here. If they were not randomly sampled, but they were randomly assigned, okay, then I can make a conclusion about cause and effect, but I can't generalize it to the population. This happens a lot, this one. Okay, it's hard to randomly select people from a population. A lot of times they get volunteers. So you have to be careful how you generalize. So the last example, does listening to music while studying improve test scores? Which of the above categories would each of these be in? So we're just going to draw arrows. We got 30 students who volunteered for an assignment or for the experiment. They were randomly assigned to 2 treatment groups. Bottom left. So they were not randomly sampled, but they were randomly assigned. Good. Random sample of 30 students. They were asked if they listened to music when studying, and then their test scores were reported. Well, random sample of 30 students. So that would be this one, wouldn't it? They weren't randomly assigned to groups. Random sample of 30 students, randomly assigned. That's pretty obvious, I think. That goes to this one. And then by the simple process of elimination, 30 volunteers. They weren't randomly assigned, they were just surveyed and measured. Okay. That's going to be important because I guarantee you're going to get a question like it on the test, where you'll be given a situation and you'll be asked, can we determine cause and effect? Why or why not? Can we generalize to the population? Why or why not? But I believe there's one like that in the review that I gave.